I'm back working on the Intel MDS systems. In this video I'll be taking a first look at one of the microprocessor boards. If you're not familiar with these systems, they're quite complex. They were developed by Intel in order to allow developers to develop the Intel processors into other systems. So these are equivalent to modern in-circuit emulators, but on a bigger, grander scale. These could be expanded into very complex systems. Very big, very expensive at the time, and very interesting architecture, but the architecture does make them quite difficult to fault find on. I'll go into more detail as to how these work as we work our way through and check the board and see if it's working okay. The first thing I always do is give the board a really good clean. This one's not too bad, but if you look at the top, it looks fairly clean until you turn it over, and then you see the bottom and you can see the difference. These are multi-layer boards. As a minimum, they've got a top layer, bottom layer, and at least a ground plane. They I think also have a power plane, but it does mean that they're quite difficult to remove chips from if you do need to swap a device. But first thing I'll do is give it a good clean, and before I clean it I want to remove the front key panel. I don't want to get anything into the keys, so this is quite easy to remove. It's a case of removing 2 screws and then loosening 3 more, but I will take the screws right out just to make sure that they don't get in the way while I'm trying to clean it. As I say, it's best to get these off before you start trying to clean anything, and that way you can guarantee you're not going to have problems later on with anything having gotten into these switches. So there's 2 screws on the front that come out, and then there's another 3 screws on here. So we'll loosen these off. We should now be able to slide this frame forward and it should release the board. So once this is free of the board itself, then the board should lift vertically out of the connectors. You need to be very careful with these connectors. They are quite delicate and you don't want to bend the pins out. These do need cleaning, so it's perhaps as well we took them out. If you need to, you can pop these keycaps off. They will just lift off the switch body, and I will take these off and give the switch a good clean. But first thing, I'll take these screws out and then go and clean the board, and then we'll have a good look at it and get some idea as to how to go about testing it. So I've given the board a really good clean. It's now looking much better. Didn't find much wrong with it. It looks in fairly good condition, no bent pins. Everything looks to be in good order. There's no lifted tracks. All the contacts are reasonably clean. Not the best quality sockets in the world, but certainly quite usable for the time. So the next step is to test all the DRAMs, and I don't know how many of these DRAMs I change every year, literally hundreds of them, and because I get through so many, I made a tester specifically for testing these. So it's very quick and easy to use. I just pop the DRAM in. These are multi-supply DRAMs, of course. There's 3 supplies for them, but it does a full multi-speed test on them and checks them at the full 200 nanosecond speed rating. The tester can go up to 100 nanoseconds if I want it to, but because these aren't 100 nanosecond devices, there's no point. So what I'll do now is pop all these DRAMs out. I'll go through them one at a time. There's only 32 of them, shouldn't take too long, and test them, make sure they're all working, and then we'll go from there. Okay, that's the last one. They all worked fine. I believe the owners of this particular machine have tested this board already. It does say OK on it, but I don't know if that just means the processor or the entire board. So hopefully I'm not offending anyone by doing all this testing, but I always proceed on the basis that they're completely untested. I never know quite what extent the testing has been carried out. So as I say, I start with the same process all the time. With a board like this, I begin by taking out and testing the DRAMs. They're the most likely fail point anyway. And while we're discussing DRAMs, it is worth pointing out that I literally replace hundreds of these every year, and mostly the failures are caused by power supply issues. So these are triple supply devices. They work on a -5, +5 and +12 volt supply. Now, because of the way these work internally, the reason they have multiple supplies is they need various voltages for the switching technology within them to operate the way it's supposed to. The problem with them is if you remove one of these supplies and leave the others in place, then the currents that flow through them internally can exceed the limits of the switching devices that are inside these, and that can cause internal shorts, and that's the usual failure mode for these. And there's many things that can cause that. Just failure of one of the three supplies, for example, can cause all the DRAMs on the board to fail. Or it might just be there's a glitch in the supply as the power came up. But in short, when I test these, I remove the DRAMs before I try to power the board up. Even if I intend to use a variac to bring the power up, if it's a machine that hasn't been used for a long time, you might want to use a variac to bring the supplies up to reform capacitors, or just test for shorts or excessive current. Again, I'd advise removing any DRAMs in the system before you do that, because if you use a variac, the supplies can all come up at different times and by different amounts, and almost certainly you'll be outside of the accepted voltage tolerances of the DRAMs, and that can damage them. So what I normally do is just remove them completely, test them, and then I know that they're safe, and I can test the rest of the board without worrying about blowing up the DRAMs. And the next step, once I've powered the board up, is actually to test all the voltages on the socket. Just to demonstrate what this will do if I put a faulty chip in here, I've got a faulty one here. It's not off this board, this is just another one I had lying around. So put a faulty chip in and it will give me a red light to indicate the device is faulty. I've shown this device before, and I've been asked how it works. It's fairly straightforward. It generates the 3 rails that are required and current limits them, but it also allows them to be completely disconnected from the ZIF socket. So when you're taking out devices and putting them in, the power is completely removed from the socket, so there's no danger of damaging them. And the same with the control signals. The processor that drives this, when it's inactive and it's not driving the DRAM, all the pins are set as floating inputs, so it doesn't put any current into the device. So it's a very safe device to use, and that was the first part of the design. What it then does, if you are not familiar how a DRAM works, it's really nothing more than an array of tiny capacitors, or what amount to tiny capacitors. And as I say, they're in an array. So on the device itself you have 2 pins. One's a row address strobe and one's a column address strobe, and they're used to select, as the names might indicate, the rows and columns of capacitors within the chip, meaning that using those 2 lines you can effectively access particular capacitors within the device. Single bit memory chip, of course, so there's only 1 bit that it stores. And because it's a DRAM, if you store information in it, then after a few milliseconds, just a few thousandths of a second, the data will be lost. So in order to retain the data has to be refreshed every millisecond or so. Otherwise it will degrade and the data will disappear. So the way that is achieved is if you read the memory contents for each row, then that will refresh the data in the device. There's circuits in here that when you carry out a read on a row, it will refresh the data that's in that row of capacitors. So the system that the DRAM's running has to have a DRAM controller, and the idea of the DRAM controller is that apart from controlling access, decoding the memory address space, it also, on a very regular basis, every few milliseconds, will read the entire contents of all the DRAMs. And it does it on a row by row basis, so the idea is that it kind of moves like a wave through the DRAM and reads all the possible addresses, and that refreshes them, and then it just keeps repeating that over and over again. And this device does something very similar. To keep the test time down, I didn't want to test each individual bit and then wait, say, 10 milliseconds and then examine the results. So what it does is it writes data, a particular data pattern, to an entire row. It then refreshes the row a number of times, and after the period that the chip is specified for, that is, in this case it's 2 milliseconds, it rereads the chip, and as long as the data that it wrote to the chip is still the same, then it's fine, and it then changes the bit pattern on that row, does the same thing again and again, as long as all the bits can be successfully changed and then refreshed and read and there's no errors, then it moves on to the next row. That's what the green flashing LED is indicating. It's indicating each row that's been moved on to. You probably can't see it very clearly in the video because of the effect of the camera shutter, but it's when it's testing, the green LED is rapidly flashing on and off. It probably looks to be flashing fairly slowly on the camera, but it's flashing quite rapidly, and each flash indicates that the next row is being tested, and it tests each row approximately every 30 milliseconds because it carries out 4 tests per row. In other words, it tests each bit 4 times. And if it finds an error, it just puts the red LED on to indicate that it's found an error, then it stops the test. You can actually test at a higher speed. Most DRAMs will fail, so if I press the key and hold it, then after a few seconds the red LED comes on. If I now release, you see the red LED comes back on straight away, indicating the test failed. And what it's doing then is it's testing at 100 nanosecond response time rather than 200, and because it's not 100 nanosecond DRAM, the test fails. Obviously if it's run at the normal speed, then it passes fine. So that's basically how this device works. It's very useful. It saves an awful lot of time in testing systems that have DRAMs. So I'll now leave the DRAMs out of this system, and the next step is to start looking at how to test the rest of it, and there's many ways I can go about doing this. The way I'll be testing these is I will remove all the large-scale devices that are in sockets. I will then test the resistance across all the rails, making sure there's no shorts, checking for failed capacitors, shorts on the board, and I'll then apply power to all 3 rails. I won't, even though the DRAM's not here, there may be other MOS devices on here that are multi-rail. I'll then check the supply currents to make sure they're steady, and then I'll start by refitting the microprocessor and see if that comes to life. It won't do much, of course, because there'll be no DRAM and all the support chips won't be there, but I want to see if the processor starts going through the motions of trying to run, and then I can start refitting the other devices. It's a fairly complex board, but its complexity is mostly because of the number of in-out channels it has. So this is mostly all in-out, and this goes through to there's a huge board on the back of the MDS that we'll look at in another video that handles all the in-out, and this connects to that, and through that it accesses all the serial in-out. And the board on the back of the machine is what controls all the in-out. It gives access to all the serial connections. It handles the connections through to the CRT. It's got the CRT driver circuitry on there. We'll look at that on another video. But as I say, most of this is really here to provide the in-out that you expect on a system like this, that it is designed to allow testing of other systems. There's a lot of interconnections required to the outside world, and that's mostly what always is for. Of course we do have ROMs, and we'll look at the way the system runs in another video, but as I say, the main thing is to test this in a way that it's not going to damage anything, and I always work on the assumption that it hasn't been run or tested for a long time. So what I'll do now is prepare the test jig so that I can apply power to these boards. I'll just quickly grab the test jig in case you didn't see it in the previous video. So this is the test jig. It's nothing more than one of the backplane PCBs with a couple of side cheeks. I may well make up a bottom bracket on this that I can fit one of the rear panels to, and the reason I want to do that is because the CRT driver circuitry is on the rear board, the in-out board, and I'd like to be able to run the boards in here and the CRT without having to have the back panel in the way. So I might arrange this so this sits on top, but we'll look at that in another video. But as I say, what I'll do now is get this organised so I can get some power applied to the boards, and once I can start applying power to the processor board, then I can start refitting the devices and see if it comes to life, and from that point on we can start branching out into the rest of the system and see if there are any faults, and we'll address the faults and correct them as we encounter them. Okay, that's it for this video. Any comments are welcome. As you can see, it's going to be a long series, but I want to take this step by step and provide as much information as I can. I won't be able to go into very comprehensive information in every single video, but hopefully we can build on the information video by video. But if there's anything in particular you want to see, then please let me know.